Okay, so we're going to pick up with this limit right here today. If you remember from yesterday, we're doing limits as they approach infinity. Here I want to see what the limit is. I'm going to factor out the largest degree in the numerator and the denominator. What's the largest degree in the numerator? X squared. So I get the limit as x goes to infinity of x squared times 8 over, and we did it yesterday? Okay. And then if we factor an x to the fourth out of the bottom, right? When you factor an x to the fourth out of the square root, it becomes an x squared. And you're left with 2 minus 6 over x to the fourth. So at this point, you see that the x squareds will cancel. And as you let x go to infinity, this will go to 0. And so you're left with 8 over the root of 2. Rationalize the denominator. By the way, on the AP exam, you will not have to rationalize the denominator. They won't make you do that. Yep, we'll do it again. So 8x squared over the root of, I'm going to take out an x to the fourth. So as I write that, I've got 2 minus 6 over x to the fourth, right? Underneath the square root, as I take a perfect square out, it's going to become its square root, or x squared. Just like if you had the square root of 50, you would say that's the square root of 25 times 2. When you remove the 25, it becomes the square root. Right? Same thing. Better? Okay, we'll look at the this one. I'm going to take an x to the sixth out. Limit as x goes to infinity of, when I take an x to the sixth out, what does it become? Yeah, so I have 2x to the third times the square root of. Remember, I took out an x to the sixth, so I have 1 over x to the fourth plus 1 minus in my 3x to the third. It's a little bit different because now I've got really 2 terms left, right? I've got 1 term and I've got a second term. What should I take out of both of those? Yeah, I'm going to take out an x to the third. So I take out an x to the third. I'm left with 2 times the root of 1 over x to the fourth plus 1 minus 3. Now we might be more convinced what this limit goes to. What does the 1 over x to the fourth go to? 0. So you have 2 times the root of 1, which is 2, minus 3. So we have a negative 1 times some large number to the third power. And so you're going to get negative infinity. Okay, as you look at these, sometimes you don't really make an algebraic argument, but rather graphical argument. So the graph of negative 3 sine of x, what's its amplitude? How high does it go and how low does it go? 3. And so as you look at this graph, you could tell that it's going to kind of do that thing. So as x goes towards negative infinity, is the y value going to kind of zero in on something? No. Limit does not exist. Cosine of 5x, what's the amplitude? Just 1. And it might, be horizontally compressed a little bit more because of the 5. The fact is, as you go to infinity, this still bounces back and forth between what 2 values? 1 and negative 1. Does it ever zero in on something? Zero in is probably a bad phrase, but the idea that it kind of starts to just hone in on one value, and it does not. So the limit does not exist. And so sometimes people are tempted if they see a sine or a cosine or anything of that nature, they're like, well, it doesn't exist. That's not the case at all, because the next one does not have just a sine and a cosine. It also has an x and a 3x. And if I factor out the x, I get the limit as x goes to infinity of x times sine of x plus 3. Let's think about sine of x plus 3. What is the smallest value that sine of x could be? -1? What's the biggest value that sine of x could be? +1. So let's look at the worst case scenario. Let's suppose that sine was -1. Then you would have -1 times, or -1 plus 3 is 2 times then a very large number. So you'd have 2 times a very large number. Everybody agree that that's the smallest that it would be? The biggest it would be is +1 plus 3, so 4. So either way, both of these go to what? Infinity, so the limit will be infinity. That was probably my worst infinity yet this year, huh? Let's try that one. Okay, there we go. That's better. Sure. The smallest that sine can be is -1. So -1 plus 3 is 2. So then you would have 2 times a very, very large number. If sine was +1, you would get 4 times a very large number. Doesn't matter whether it's the smallest value that sine can be or the biggest value that sine can be. Either way, it's going to end up being a very large number. Okay? All right. Now, last hour we did a checkpoint over this. Can we skip the checkpoint and go to today's lesson? You're going to get a full workday tomorrow, and then I'm going to also get you the study guide tomorrow. You will have a short lesson on Monday. We use Tuesday and Wednesday as workdays for the study guide. It is pretty lengthy. We will test on Thursday. Fair enough? That is the schedule. Okay. So now we turn to curve sketching. So we're going to apply this, and why did you've already done a little bit of curve sketching, but now we know a little bit about end behavior. We're going to start by talking about domain. And when you look at a function, you want to be able to have a general idea of what it looks like. If it's a polynomial, say like y equals x to the third plus x squared, then the domain is going to be all real numbers. Most of the functions that we look at have a domain of all real numbers. But suppose it's a function like y is equal to 1 over x minus 2. Well, what's the issue there? Can't have 2 in the denominator. So the domain is all numbers not equal to 2, or x not equal to 2. And if you have, say, y is equal to the square root of x, well, then you can't take the square root of negative numbers. So you'd say the domain is going to be x greater than or equal to 0. So we did that last year, right? Yeah, and so it kind of brings it back a little bit. Range, really probably not that important. Once we find the domain, we'll probably be able to figure out the range. But intercepts, well, that's a different story. Intercepts are super important. And we know how to find y-intercepts. Y-intercepts, you just plug in 0 for what? The y-intercept is going to happen where x is equal to 0, and then you're going to have some y value. As the x-intercepts, you're going to plug in 0 for y, and you're going to get some x value. Okay? And actually, you took that test last year. I have it right up here for the college algebra class. They just had their test. They're feeling pretty good about themselves. So, you found all those solutions using rational roots theorem and everything else. You're pretty good at that stuff. Symmetry, we were not going to talk a lot about, but some functions do have symmetry. For example, y equals x squared. That's symmetrical about what? What's it centered around? X equals 0, the y-axis, yes. Yep. And if you did y equals x to the third, well, that's symmetrical about the origin. If you're flipping 180 degrees, it'd be symmetrical. We won't go through the business of testing for that, but if you recognize it's something symmetrical, use that to your advantage. Asymptotes, super important. You're going to look in this case like, let's say you have 2x plus 1 over x minus 3. Do you know what the vertical asymptote is going to be? Where is it? Undefined. The horizontal asymptote is going to be based off of what we covered yesterday. So the idea as x goes on towards infinity will create a horizontal asymptote for this rational function. As you move this on to infinity, what's the biggest term in the numerator? 2x, and what's the biggest one in the denominator? If you take 2x and divide it by x, you get 2. And so the horizontal asymptote will simply just be 2. If we were to take that limit, that's what we would get. And we'll go over that together more. But let's get back to the stuff that we learned just earlier so we can compare this all together. We also want to talk about intervals of increasing and decreasing. And maybe remember that f prime of x is increasing wherever it is greater than 0, and is decreasing wherever f prime of x is less than 0. That's where we'll be decreasing. How do we determine if it's a local max? Where f prime of x changes from positive to negative, and a min where it changes from negative to positive. Now, for concavity, do I use the first derivative or the second derivative? I use the second derivative. The second derivative test tells me concavity. Wherever the second derivative changes from negative to positive, or where the second derivative changes from positive to negative, would give us, that would give us our points of inflection, right? That's where it changes concavity. It's concave down wherever f double prime of x is less than 0, and it's concave up wherever f double prime of x is greater than 0. All review, right? So the cool thing is that we get to piece it all together and build with it our one last thing, which was from yesterday, and that's regarding end behavior. The end behavior is what happens as you take the limit as x goes to positive or negative infinity of the function. And once we can determine that, then we know what it looks like as it goes on forever. Which is a neat thought, you know. If you sit down and try to think about forever, it starts to hurt your brain after a while. You know what I mean? So you just pick points in time. You're like, wait, I got to go further. Anyway, so, all right. Let's do the example. Use the following guidelines to sketch the following curve. On your test, you can use your calculator, but you cannot graph it. You can use your calculator for computation, but you cannot graph it. Or you can say you can't use your calculator at all. All right, sounds good, Wally. So let's go. I would like to start at the intercepts. I'm going to find the y-intercept. The y-intercept occurs when x is what? Okay, if we put 0 in for x, we get 0 for y. Now for the x-intercepts, I have to set the function equal to 0, or 0 is equal to x to the third minus 2x squared minus 3x. Can I solve that? Take an x out, 0 equals x times x squared minus 2x minus 3. So I have x minus and x plus 1. Sweet. So I have x-intercepts of 0, 3, and negative 1, it looks like. Awesome. This isn't a rational function, is it? So I'm not going to have any asymptotes. But I am going to have end behavior. Okay. The limit as x goes to positive infinity and the limit as x goes to negative infinity are going to be values that I can figure out. We did that yesterday, right? Now, we're all about saving time, right? Can I save you some time? On the test, I'm going to have you guys actually do the work for showing me the limit as x goes to infinity. But when you get to the curve sketching stuff, you don't have to show all your work. You could just determine it however you want. This is a cubic. So does it end up or end down? It's positive. Ends up. So it'll begin down. It's going to look something like that. I mean, we all know enough mathematics to say it looks something like that, right? So as x goes towards positive infinity, y goes towards positive infinity. It's finishing up. And as x goes towards negative infinity, y goes towards negative infinity. So just the knowledge of the general shape is enough, okay? I'm not going to make you factor out the x cubed and show your work there. I will on other parts of the test, but not for that. Fair enough? Okay, so we've got a really good idea of some end behavior and intercepts. Let's now do intervals of increasing and decreasing concavity. So what am I going to have to do to figure those out? Derivative. So f prime of x is equal to, what is the derivative? 3x squared. Sweet. Does that factor? I wish it did, but it doesn't. So because it doesn't, what do I have to use? Quadratic formula. Somebody take your calculator, quadratic formula, type in 3, -4, -3. We'll leave it to Maddie. Awesome. Now, I showed you yesterday that we could test points, correct? But there's another way to do it instead of testing points. I could consider the graph. What shape does it make? Parabola, right side up or upside down? So, am I positive or negative? Positive, negative, and positive, right? So, that saves you time instead of testing points, correct? Again, we're all about saving time. Now let's do the second derivative. F double prime of x is equal to what? 6x minus 4. Where is that equal to 0? 2/3. What shape does that make if you were to graph it? A line. Positive or negative slope? Positive. So it looks something like that, right? So it's negative here, it's positive there. Quicker than testing points, right? So use the graph to your ability and state that. Great, we did the first and second derivative test. We can now state the intervals of increasing. Where is it increasing? Good. Union with 1.87 to infinity. Where is it decreasing? Between those, right? So I'm going to stay with the first derivative. Where do I have a local maximum? Why do I have it at negative 0.53, Claire? Because the first derivative changes from positive to negative. So therefore, I have a local min at, good. And I have an inflection point. That will be determined by what? The second derivative, where it changes sign, and it changes sign at 2/3. Good. So we'll figure out y values there in a second. First, concavity. It looks like if I check out my second derivative test, I have from concave down from negative infinity to 2/3, and then concave up from 2/3 to infinity. So this is part of the reason why I'm giving you your calculator on the test, is because I don't want to try to write, problems that is going to, make you where you just come up with integer values and stuff, and or maybe fractions are fairly simple to compute. Here when we type in our function, we're going to get, kind of messy results, and that's why you can use your calculator. So x to the third minus 2x squared minus 3x, and if I go to my table, type in negative 0.53, 1.87, and 0.66. And there's my outputs. I have 0.88, negative 6.1, and negative 2.6. Is this enough information to now sketch an accurate graph? It is a ridiculous wealth of information. We have never accumulated this type of information before. Our graph is going to be so good, you're going to want to take a picture of it afterwards and send it to Grandma. So we'll do it. What'd you say? Did he say doubt it? Somebody vote him off. Okay, so I made the x values by 1 and the y values by 2. So that's how I choose to roll. My x-intercepts are negative 1, 0, and 3. And last year, you would just use the x-intercepts and you would sketch it, but you never knew how high the max was or how low the min was. Now we have conclusive evidence of exactly what that is, negative 0.53 to 0.88, which is, I'm sorry, so I made a tick mark every 2, so that's going to be a little bit less than half. And then, let's see, 1.87, so that's over here. Negative 6, right about there. And then 2/3, negative 2.6, right about there. And we know it starts by increasing those are from my x-intercepts that we determined originally. When we get back, we'll check that out. We have one more example left. All right. I'm going to type this into my calculator, folks. All right, what do you guys think about my graph? Pretty much money on. There you go. All right, flip it over. One more problem. Jake Bordwick said this was his favorite problem ever. No. No, so I'll show you exactly what you can do. So here we go. We got f of x equal 3x over x plus 2. What's different about this function compared to our first one? Have asymptote. Vertical asymptote at what? X equals negative 2. Very good. Now, as I consider the end behavior will be determined in this situation by a horizontal asymptote. Yes. Oops, sorry. Scroll in the wrong spot. So we got vertical asymptote at x equals negative 2. Now, as you look at this function, as I take the limit as it goes to infinity, here's all I have to do. What's the largest term in the numerator? 3x. What's the largest term in the denominator? X. Divide them and you get 3. So that means that that's going to be the horizontal asymptote. If you carried out the limit as x goes to positive and negative infinity, you would get 3. If you don't believe me, just do the work and you'll see. Now, let's talk about intercepts. The y-intercept happens when x is equal to 0. Plug in 0 for x and you get 0 over 2, which is 0. Now, for the x-intercept, you set the function equal to 0. 3x over x plus 2 is equal to 0, or say 0 over 1. Now, here's something I'm going to refer to throughout the course of the next few days, but that is, if you want to determine where it's equal to 0, am I looking for where the top is equal to 0 or where the bottom is equal to 0? top. Why? Cross multiply. Look at what you get. You get 3x is equal to 0, right? That's the same thing as just looking where the top is equal to 0. So when you're wondering about the x-intercepts of a rational function, just look at the numerator. Where is 3x equal to 0? It's 0. If it was x minus 2 over x plus 3, then it would have an x-intercept of positive 2. The x-intercept happens when the top is equal to 0. Okay? All right. Now, in order to do this stuff, we need to take the derivative. In order to do this derivative, I need to use what rule? I could do the chain rule with the product rule, but I would have to write it as 3x times x plus 2 to the negative 1. So that'll be product with the chain. Instead, I'm going to choose to use a quotient. Derivative of the top times the bottom is x plus 2 minus the top 3x. What's the derivative of the bottom? 1. All over x plus 2 quantity squared. What does the top simplify to? 6. Now, I'm wondering, is that ever equal to 0? Is the top ever equal to 0? No. So this is never equal to 0. But I shouldn't just include where it's equal to 0. I should also include where the derivative does not exist. At what point does the derivative not exist? Negative 2. So I will check on either side of negative 2. I'm going to plug in negative 3. But first, as you look at this, if I square something, that's going to always be positive. And the top is always positive. Positive divided by positive will be. So it doesn't matter what you plug in. I promise you, you'll get a positive in either situation. Yes. Well, if we set it equal to 0 to find where it's equal to 0, you're not going to get a result. You're going to cross multiply and you'll get 6 is equal to 0, and that's never the case. So we choose to set a point of negative 2 because that's where it's undefined. Now, we already have our intervals of increasing from negative infinity to negative 2, union with negative 2 to infinity. When is this function decreasing? Never. Where's the local max? There are no local maxes. How about local mins? There's none. So in order to do concave up, concave down, and inflection, I need to find what? Second derivative. So 6 over x plus 2 squared could be rewritten as 6 times x plus 2 to the negative 2. What rule would I use then? So f double prime of x will be equal to, use a chain rule. We've got 6u to the negative 2 and x plus 2. Derivative is 1. Derivative is negative 12 over u cubed. So I have negative 12 over x plus 2 cubed. Is that ever equal to 0? No, it's not. It's undefined at negative 2. Will it always be positive or always be negative? It always changes, right? So if we try plugging in, say, negative 3, we get negative 3 plus 2 is negative 1. Cubed is negative 1. Negative 12 over negative 1 is positive. And if I plug in 0, I get 0 plus 2 is positive. Cubed is positive. And then negative divided by positive negative. So I have concave up from concave down from negative 2 to infinity. Is there a point at which it changes inflection? But is negative 2 part of our original domain? No. So some people will say there's an inflection point at x equals -2, but if you were to plug in -2 to come up with a y value, you can't get one. So therefore, we say that there is technically no points of inflection. But if you were to list x equals -2 as a spot that it changes, again, it's inflection point, and that's not a point. But if you're just telling me, well, -2 is going to switch, I understand what you're saying, and I won't mark that wrong. But technically, this does not have an inflection point. Well, now we can sketch it. We have intercepts at 0, and I'm going to have 1, 2, 3, 4, 1, 2. Vertical asymptote at -2. Horizontal asymptote at 3. I have x and y intercept at the origin. So I know it goes through there. And if it's always increasing, is it going to be over on this left-hand side? Is it going to be in the top or the bottom if it's always increasing? It's going to be in the top. Again, all this should match up. It's always increasing. It's concave up. Here it's concave down. It should always match. A quick sketch it, see what I get. Three x divided by the quantity x plus 2. Window. Let's go zoom standard. It's pretty good. No matter what the directions say, carry out what we did, okay? We didn't look for symmetry. We didn't always state the domain. But we did look for asymptotes and behavior, intercepts, intervals of concavity, intervals of increasing and decreasing. Again, tomorrow you're going to have a full work day, okay? So tomorrow's going to be time to get caught up on your infinite limits as well as these graphing pieces. And then, we'll see what the weather does next week. Sounds like we're supposed to, we're in the 24 to 40 inch range, you're saying? Wait a minute, and when is this scheduled for? Okay. But it's in Iowa right now? Oh, okay, got it, got it. So it was supposed to really hit Iowa, and now since we're just 13 miles north of Iowa, it's projected to go a little bit further north. So the Twin Cities might not be looking at much, but we might. Okay, and then it might just go completely over us and get up to Canada. Okay, all right. You goofballs.